Okay, now we see that PV equals big N times K times T, where big N sub A, well, not where. We're going to let big N sub A stand for Avogadro's number, which, as you know, is the number of molecules or particles, atoms, in a mole, depending on what kind of a gas you have. And we usually use this with gases. Actually, we use it with all kinds of substances in all states. In any case, if Na is Avogadro's number, what we're leading, of course, is big N has to be related to the number moles little n, so we can relate PV equals big N KT to PV equals little n RT. Okay, so the connection is that big N's the number of molecules. This is Avogadro's number. If we divide both sides of this equation by Avogadro's number, we get PV equal over Na equals N over Na KT. And N over Na, of course, is the number of particles in the gas divided by the number of particles per mole. And what's that give us? We divide the number of particles by the number of particles in a mole. It just gives us the number of moles. So we end up with PV over Avogadro's number equals little n times K times T. Well, that's still not little n RT, but it's getting awful close, because what we do next is multiply Na by both sides and absorb that in with the K and the constant here. So we have little n times K Na times T. And now we got PV equals N times something times T. From careful measurements, we know that the something here is R, Rydberg's constant, or the gas constant, and that equals K times Na, which relates K to R. Kna equals R, so K is just R divided by Na. And that's how we get Boltzmann's constant from our empirical results for the gas constant R. Now we can express the gas law either this way or in the PV equals little n RT. If we express it this way, remember that PV was equal to N times 2/3 the average translational kinetic energy. Now you can't see it, this little subscript in kinetic energy here is now translational, because we're getting into the problem that can also be kinetic energy of rotation in diatomic molecules. So I'm going to be specific here about this. I wasn't specific before, but this is now translational kinetic energy. Okay, so temperature is related to the translational kinetic energy, and as we saw before, again, what we call temperature turns out to be 2/3, PV equals big N times 2/3 of the average translational kinetic energy. This means that this quantity here must be equal to KT. Average translational kinetic energy is then expressed in one of two ways. Okay, we can say that this should be divided by N here. I was anticipating the total energy. What I'd written there is the total translational energy, kinetic energy. Okay, average translational kinetic energy, we see from setting this equal to PV and then solving for kinetic energy, is 3/2 times PV over N. That's one expression. The other is what I was alluding to a minute ago. This is equal to this. Whatever is multiplied by N here is equal to whatever is multiplied by N here if we have a true equation, so that the average translational kinetic energy is 3/2 KT. This allows us to determine the average translational kinetic energy of a molecule if we just know the temperature, because K is that universal constant, 1.38 times 10 to the negative 23rd joules per particle second, particle Kelvin. Okay, given T then, we can get the average kinetic energy of a molecule. We can also since the total kinetic energy is just the number of molecules times the average kinetic energy, multiply n times the average translational kinetic energy here, and see that the total translational kinetic energy is 3/2 PV, just what I had written here without the n in the denominator. So we've got two important results. One is the average translational kinetic energy of a molecule, which will allow us to predict the speed of a molecule if we know its molecular composition. And the total translational kinetic energy, total internal energy, translational internal energy of the gas in a system at a given temperature. Well, at a given pressure and volume. We don't even need the temperature, and that's what's neat about this. You give me the pressure and volume of a gas, I'll tell you how much translational kinetic energy there is in all of its molecules.